Yeah, so you see, I'm trying to cover two topics here today, which is going to be quite a task in just 10 minutes. And from the title, you can already see it's going to connecting the last talks with the next talks, I hope. And it's also similar to the introduction talk you heard already this morning. So usually when I give astrobiology talks, I start with that old Hindu story or legend about the blind man and the elephant. So as the story goes, a handful of blind men find an elephant and try to figure out what that thing is. And one guy starts to grab the tail and thinks, yeah, that feels like a brush or like a rope. And the next guy touches the leg and says, yeah, that must be a tree. And the third guy touches the side and thinks, that must be a rock. And I think in astrobiology we are pretty much doing the same thing. Just as we connect all that, the information and connect our knowledge and the information we get, then we can only answer that question of life in space. So all alone in our fields, we are pretty much blind, so we really have to connect, and that's why we go to meetings like that one. And actually, we're in like the greatest, best times to do so, at least for astrophysicists, and I guess in your field it's probably similar. So we are finding planets that were really science fiction just a couple of years ago, and even in our next neighborhood in Alpha Centauri, we are finding planets, and we're also finding them in so huge numbers that we can, in fact, write periodic tables of them. So a couple of years ago, we only found these really hot, far out, close-in Jupiters, and in the last couple of years, we moved that way inwards to the smaller ones and colder ones. So we can really start to compare these guys. And as you've seen in the talks before, one of the techniques to compare them is that transit and eclipse method, where you observe light curves and preferably in different wavelengths. So you either use photometers in different wavelength channels, or you use a spectroscopic instrument and bin down the resolution. And then you get, as we've seen in the talk before, you get like a spectral data point at the wavelengths of your light curve that represents in the dark spots here, and then you take different models, in this case water plus methane, and water plus methane and CO2, and with these models you can talk about the atmospheric composition of these guys, what their structure is, sometimes even their formation history, and so the connection to astrobiology is with next generation instruments and platforms, or maybe next generation instruments and platforms, we might even be able to observe biomarkers when you biologists agree on biomarkers. So that's what we're going to do in the future, hopefully. So that's why this technique is so important. And as you've seen in the two talks before, so far most of that science was done by space telescopes for the stability, because the Earth's atmosphere is absorbing exactly these molecules we're looking for. And one of the projects, or my main project that I'm working on, is to export that technique to other platforms. And one thing, and one of my most favorite projects is working with SOFIA, and I'm not sure if everybody of you heard about SOFIA. That's actually one of the big new telescopes, or not that new anymore, but just started a couple of years ago to observe. It's basically a Boeing 747 with a 2.5-meter telescope on board, and it's a joint venture of NASA and the German Space Agency. And as you can see here, there's kind of a big garage door on the back of that plane that opens, and then you have that 2.5-meter telescope behind that door. And in principle, it's a space telescope that comes home every morning. So you can put on new instruments, you can put on dedicated exoplanet instrumentation, and that's one of the things I'm working on and hoping to transport that technique from the space, at least to these airborne platforms. And then the next step, another thing that I'm working on, is doing this stuff from ground-based telescopes in Hawaii or in Chile. At the moment, we are hoping that multi-object spectrographs are the next breakthrough from the ground to do these observations, and all of us are, of course, also looking forward to the 30-meter class telescopes that will come up in the future. Yeah, I could talk about SOFIA forever, but maybe next time. So moving on and asking what are the most promising targets. And this morning we already heard that down here at the end of the main sequence, the really small and faint ones, these are the most promising guys for us, at least for the beginning. These are probably the first ones, or the first exoplanets in the habitable zone that we can really take spectra of with the method we've shown before. And just to repeat that, what are the advantages of these red dwarf stars in comparison to the sun, or even bigger bigger giant stars. So one advantage is their low mass. So that gives a couple of advantages for detection methods. You can imagine that Doppler wobble is going to be much bigger if you pull on a small star than if you pull on a big star. This guy doesn't even move if a Jupiter is pulling, but this guy is really shaking back and forth if a star is pulling. And the other thing is, like, if you imagine a transit of a small Earth here, of course the transit signal is much bigger if you transit around these red dwarf stars. The other thing is, as we've seen in the habitable zone plot, is that the low temperature of these stars brings in the habitable zone. So one advantage is, if you see a transit of Earth around Sun every 365 days, you might see a transit of a habitable planet around these red dwarfs every 10, every 50 days. So you can just take way more data than on an Earth-like planet. Then just statistically, most of the stars in the solar neighborhood in our galaxy are actually M-Dwarf stars. So 70–80% of the stars are M-Dwarfs. So it's just statistically a way bigger chance to find habitable planets around these guys. So that's another advantage. And one of the results from the Kepler mission is that, in fact, these stars tend to have more planets, at least within these short periods, than other type of stars. So lots of advantages, but however, there's always a catch. That's why the asterisk is here. And we heard that already this morning. These guys are tidally locked. So as we've heard before, they do what we call a synchronous rotation. They always face the same side to their central star, just as the moon is always facing facing the Earth with the same side. And that can, in fact, lead to some funny effects and some funny models for these kinds of planets. And one of them is the so-called, or what we call, eyeball Earth. So you have the star here that's always radiating to the same side of the, in this case, like an icy eyeball or icy Earth. And you can see that this part that's always showing to the Earth has an open ocean, and the rest is frozen over like Europa. And this is one scenario how these planets might look. But there are a couple of other scenarios. You can have like just a rocky ball that is hot here and cold there. You can have one guy with a magma ocean here, and if it's more rocky planet with less water, you might have a desert here and some kind of rivers on the edge and ice on the back. Or if you have an atmosphere that effectively transports the heat to the cold side, it might more look like that one. So this is one possible scenario how these tidally locked habitable planets might look like. And in fact, we already found some guys who might be like that. So for example, these eyeball Earths actually are a model for GJ 581G, and we also think that Kepler 10b and Kepler 20e might more look like these eyeball magma guys. So again, just one example how these guys might look. There might be other models, but just like a nice elephant for us to everybody can put their ideas into that environment. And that's also basically my message. So at the SPARSAS, you might have heard about that Sao Paulo Astrobiology School. We had a research focus group project, and the group that I worked in, we had that project to build up a simulation chamber to exactly to simulate these environments. So that 24/7 radiation of a fainter star, to see what that does to, for example, extremophiles from analog environments. And here again, we need the input from all connected fields. We need chemistry to talk about the composition. We need atmospheric models. We need the observers to really tell what the incoming radiation of these M-Dwarfs is. So it's really one of these elephants where we all have to put our information in, and therefore all of us get their certain information back. So we can talk about the habitability of these environments. We can eventually derive biomarkers if we see what kind of changes these extremophiles do, for example, to the atmosphere. And what's important for us observers, we really get target decision guidance for upcoming platforms. We know which guys to look for and which guys might not be the best ones to look for. And the take-home message with that is just take your favorite lab thought experiment and put it in that M-Dwarf tidally locked Earth environment. And that's where I stop my talk. Thanks. That's actually a good question. So the question was, how long do M-Dwarfs live? That's basically your question, right? So in fact, they are the longest living stars. So they have a much longer lifetime than G stars or F stars. Like they can get 5 to 10 times, depending on their mass, they can get 5 to 10 times older than the sun. And that's actually an advantage for life, because it would have very much time to evolve, to stay, or to evolve to higher stages. The other thing is, one backdraw for these guys is they might be very active. So whatever's living around the M-Dwarf needs to develop a technique to deal with sudden UV outbreaks. So there's kind of a trade-off. But we think, or I think, that these M-Dwarfs might be really good targets.